Hi, welcome to a new session of control systems. In today's class, we are going to see time response analysis, and this particular session we are going to treat as class 1. So for under time response analysis, when you see transfer function for a given system, for example, you have input R of S, output C of S, you have a gain and you have a feedback path of H with negative over here. Then the transfer function, that is the closed loop transfer function, denoted by CLTF, is given by G of S by 1 plus G of S H of S. Also, we treat this closed loop transfer function as transfer function C of S by R of S, which is equal to G of S by 1 plus G of S H of S, where C of S is the output, R of S is the input. So R of S is the input signal, and in control systems, standard test signals are used as input signals. So what are these standard test signals? You have a step signal or unit step signal, a ramp signal, a parabolic signal, and an impulse signal. So these are the standard test signals what we see or we come across in control systems. So we have to know the basics about these test signals, and we should know how to employ these signals whenever you are dealing with control system. So the standard test signals, how they look like, if you take a step signal, the R of t is plotted versus t, which is nothing but equivalent to A. You can see there is no variation in the uh, uh, graph of A when time is also is varying, but A is not varying. So R of t is equal to A for t greater than equal to 0, and R of t is equal to 0 for t less than 0. This type of signal is known as step signal. And if at all you replace A by 1, it becomes unit step signal for the same variations of t. When you take about a ramp signal, and if at all you plot, you're going to see that ramp signal resembles equation of a straight line passing through origin, where R of t is equal to y, and t will be replaced by x, and slope will be given by this line which is passing through the origin. So if at all you plot different values of t, you're going to get different values of R of t. So R of t is equal to AT. Now here A is the slope and t is greater than equal to 0. For that the value of R of t is AT, and R of t is equal to 0 for t less than 0. When you replace A by 1, it becomes unit ramp signal. When you take a parabolic signal and you're trying to plot its graph, the equation is given by R of t equal to A t square by 2 for t greater than or equal to 0. Means what? If at all I take the value of t as 1, I'm going to get R of t is equal to 0.5a. And let me take the value of t equal to 1.5, then the value of R of t would be equivalent to 1.125a. Similarly, if at all I take the value of t is equal to 2, then I'm going to get here the value of R of t as 2a. When I'm going to plot this graph, it would be in this fashion. So parabolic signal resembles this kind of waveform. So for R of t will be equivalent to 0 for t less than 0. You replace again a with 1, it becomes unit parabolic signal, and that is how the variations of time is done. Whereas a special case called as impulse signal, denoted by delta of t, when you plot this graph, you're going to see that delta of t is equal to 0 for t not equal to 0, and delta t is equal to infinity for t equal to 0. So this is how the impulse signal is framed. We are going to see importance of impulse signals in our coming classes. As of now, you remember that it's a kind of high amplitude signal for t equal to 0. So these are the standard test signals. When you are going to see the analysis of time domain, and when you convert this time domain into frequency domain by applying Laplace transform, for example, you have a step of a unit step signal of 1. For its time domain equation of A changes to Laplace transform of R of S is equal to A by S. And if at all you have A replaced by 1, then it becomes 1 by S. This formula you should remember. And this tabular column is very important. If at all I take the value of ramp signal as AT, then Laplace transform will be equivalent to A by S square. For unit ramp, it will be R of t equal to t, and Laplace transform of this value will be 1 by S square. If at all you take the parabolic signal, it is AT square by 2, and Laplace transform of this signal will be A by S cube. For unit parabolic, it would be 1 by S cube. And for impulse, delta of t is equal to delta of t is nothing but the peak value when you are going to reach for t equal to 0. So its Laplace transform would be 1. So this particular tabular column you should remember in order to solve all the problems which are related to test signals, and you should know how to convert them into Laplace transform or inverse Laplace transform. The basics of Laplace transform and inverse Laplace transform you should learn when you're dealing with control systems or signals and systems. Anyhow, this is a important basic, and you should remember all these formulas, and you should know how to apply Laplace transform for different types of signals given to you. Another important point, if at all you look into the table, integration of step signal will resemble as a ramp signal. You see here step signal, if at all you integrate this value, the answer would be equivalent to ramp signal, and if at all you integrate ramp signal, the output would be parabolic signal. So this important note you should keep in your mind. Let us employ a test signal, that is unit step input given to a first order system. What is meant by first order system? For example, if at all you have the g of s replaced by 1 by st and a feedback is given as unity. So this type of controller design where you have only the power of s as 1, the order of what we call here. So this type of system resembles the first order system, and it is given in the concept that you have a unit step input, that is r of t equal to 1, and what we know that the Laplace transform of r of t is equal to r of s, whose value is nothing but 1 by s. This is an important catch over here. Apart from that, you have c of s by r of s, which is given by g of s by 1 plus g of s into h of s. Here the value of h of s is 1 and g of s value is 1 by st. So if at all you take this numerator and denominator value, and if at all you simplify it properly, you're going to get 1 by st plus 1. Okay, and we know that the value of r of s is nothing but 1 by s. Okay, so I'm taking this r of s onto the right side, and the value is 1 by s, that is r of s value. So c of s is equal to 1 by s into st plus 1. So you have to make them into a proper fraction. So for that I'm taking t outside, so it becomes st of s plus 1 by t, and I'm taking this 1 by t onto the numerator. Thus you are done with proper partial fraction values given by a by s plus b by s plus 1 by t. Now these equation 1 can be solved by partial fractions by taking the value of a equal to s multiplied with the given transfer function, that is 1 by t by s into s plus 1 by t, and substitute the value of s is equal to 0. So this s and this s will cancel out, and you have to substitute s is equal to 0. So s will be substituted over here, and you're going to get the value of a equal to 1. I hope you understood how we got the value of this value of a, that is equal to 1. Similarly, you can get the value of b by taking the transfer function 1 by t by s into s plus t multiplied with s plus t, and substituting s is equal to minus 1 by t. So you can see b is equal to s plus 1 by t, and the transfer function given as 1 by t by s into s plus 1 by t. So this s plus 1 by t cancels in the numerator and denominator, and you are left out with 1 by t divided by s, and you have to substitute s is equal to minus 1 by t. So we're going to get the value of b is equal to -1. Thereby, equation 1, C of S, by replacing the values of a and b, can be obtained as equation 2, like C of S is equal to 1 by S minus 1 by S plus 1 by t. Now you need to employ inverse Laplace to equation 2, and you are going to get the value of C of S is equal to C of t. 1 by S is nothing but inverse value is 1 minus 1 by S plus a, where a is equal to 1 by t. When we treat, the value will be equal to 1 minus e to the power of minus t by t. This is a capital T. Uh, so this is how the equation is obtained of C of t. So it is treated as equation 3. Now carefully better you observe, C of S is taken as 1 by t divided by S into S plus 1 by t. This equation 1 is changed into equation 3, where input is R of S, and that is being utilized in the formula of C of S. And finally we got the value of C of t. So the input given to the system is unit step input. So this is the unit step input given to the system, and we got the output C of t, which is 1 minus e to the power of minus t by t, capital T. So the value of it all is substitute the values of small t equal to 0, t, 2t, 3t, 5t. So this is how you are going to get the graph. So you plot the graph, you are going to get the graph which is exponentially rising in nature. So input is step input, output is exponentially rising. So that is the beauty of this concept. So different type of signals can be given as input, and pertaining to that, output is obtained in different fashion. So you please try to employ unit ramp or parabola instead of R of S, and comment in the chat box what output you are going to get for C of t. So we are going to deal with this concept further in our coming classes. I hope you like this session. Please share among your friends, subscribe to this channel, and press the bell icon for future notifications. Thank you.